Okay, yeah. So once again, good evening and welcome to our CodeCamp webinar on data structures and algorithm. Okay, of course, this is actually going to be a series. So this is going to be the first part, but of course, I'm going to leave the whole introduction to uh, uh, the person who's going to be taking us, of which I would love to introduce him, but I really don't. I still don't know how to do. The best way to actually introduce him. But of course, he's my boss. He's none other than CEO of Code House. And of course, joining this call also, let me recognize the managing director of Code House in the person of Mr. Engineer Radha Lawrence Akube. And also joining this call is the admin of Code House, Mrs. Imabong John. So it's actually interesting to see, you know, these interesting and amazing individuals join us for this session. So a huge welcome to every one of you. I want to believe I'll see you in the next session and in the session to come. So that being said, I think I'm just going to hand over to Engineer Aniebiet to take over this webinar. So Engineer Aniebiet, over to you, please.
Right. Thanks, IK, and good evening, everyone. Welcome to this. I wouldn't call it a class. It's a webinar. So, because I'm not really teaching, even though I'll go through a lot of stuff that will make it seem like I'm teaching, but it's more of a discussion, an opportunity for everyone to learn. Yeah, algorithms are essentially at the center of our lives right now, as far as the internet and the tech age is concerned. So it is very important that everyone, and I say that very seriously, everyone who wants to step beyond being, at the lowest level of tech, everyone needs to familiarize themselves with algorithms and what they actually mean. So having said that, I'm going to share my screen and then we will just go through an introduction. So confirm that you can see my screen. Confirm that you can see.
Yeah, I can see your screen.
Yes, sir, I can see your screen.
Okay. Yeah. So this session is really, I want to start out by saying that it's not going to be enough for any of us here who hasn't already become an expert in algorithms. It's not going to be enough for you to become an expert in algorithms. But the idea is to actually help us kind of point us in the right direction. So the expectation is that at the end of this series of webinars on algorithms and data structures, that at least we'll understand what it entails, what it involves, and how we can get better. In fact, as a matter of fact, while I was doing research for this presentation, I came to realize that there are even a lot more things. Somebody like me personally, I still need to learn on algorithms, and I'm now even more interested in picking those up. So you can't, just like any other thing in tech, just like programming, whether it's backend, front end, or design, or even digital marketing, or any of these other things, right? You cannot become an expert overnight. You cannot even become an expert in 6 months or even in 1 year, but it takes consistent study. And the algorithms is the same. One thing I want to tell everyone, as far as this algorithms thing is concerned, it's not constrained to any particular set of people, right? Even people who, yeah, we know it's developers. It doesn't matter your tech stack, whether it's backend or front end or whatever programming language you are focused on. These are general principles of computer science and they apply to everyone. But what I even want to go further and say that it also applies even to product designers, right? And even digital marketers, it's good to understand how these things work. You may not delve deeply into them, but at least having an understanding, of what algorithms is helps you think better about, when you are doing marketing or when you are designing stuff. Okay. So having said that, this series is a 5-session series. Today we are just going to do one session. We'll do the remaining 4 sessions in future, or the days will be communicated to us. But these are the topics that we'll be focusing on, just kind of trying to touch through them. So today we'll be looking at the first topic, which is introduction to algorithms and data structures. So today is really going to be introductory, and we'll be having a lot of discussions. We're not going to delve deep into too much of the mathematics and all of the other things, right? But it's just for people to get comfortable. Because one thing I seem to see is people actually get scared and run away from algorithms because maybe they feel there's too much maths in it. But once you make it clear that this is really just a representation of things that we're already doing intuitively. So I will be trying to make sure that everybody gets an intuitive understanding of what we are doing here, what algorithms is about, not just going into maths. And I'll try to minimize the mathematics as much as possible, but we can't run away from it. But anyway, for today, we will not even delve into all of that. We'll just be discussing about it in general. And like I say, it's going to be more of a discussion. So I'll be asking questions. I'll ask people to make their comments either on the chat or to vote or to bring in their own solutions, right? So having said that, we'll delve into that. Number 1, introduction to algorithms and data structures. The remaining 2, 3, 4, 5, we will do later. All right. Okay, so yeah, this is the entry slide for this. What are we going to talk about in this the first session of this series? We'll talk about generally what is an algorithm. We'll talk about the history of algorithms. Where did they come from? Then we'll delve a bit more into algorithms. We'll talk about the different approaches for solving algorithms. Then we'll talk about big O notation, which is very important when you want to measure the quality or performance of an algorithm. In fact, complexity. Then we'll talk about how you code algorithms, because one thing is for you to design an algorithm, the other thing is to code. Somebody can design and you code, or you could design, somebody else codes, or you could do the two. Then we talk about data structures. Data structures are very important, but the data structures we are talking about here will be like an overview. We would dwell more deeply in data structures in the next webinar. Then we'll just discuss some simple algorithms and maybe take some exercises. Okay, so now what is an algorithm? And I want us to, this is like a discussion, okay? So what do we think? An algorithm basically, right, is in simple terms, a series of steps that you follow to carry out any task or to solve any problem. So when you look at that very simple, simplistic definition of an algorithm, right, you come to the conclusion that almost everything you have done or you ever will do or you may do can be expressed as an algorithm. And this is true. In fact, if somebody tells you open the door, what most people don't understand is that just standing up from your seat, going over to the door and opening it is actually an algorithm. But your body has internalized it and you have become so used to it, you do it without thinking. But if somebody were to ask you, list out every single step that you take, every single thing, in that process of you standing up from your seat to go and open up a door, list it out in pseudocode or write it in JavaScript or Python or C++ or whatever language. That's when you start realizing that it's actually challenging. So the human brain is already very good, and we already apply algorithms in our day-to-day life without realizing it. So, yeah, algorithms are everywhere. It's not just in computer science. In computer science, it is formalized, and that's why it looks difficult. And when it's formalized, it's put into a symbolic language. And when we look at that symbolic language, we begin to, because we don't understand the symbols, it's just like not understanding any programming language or a particular programming language, and it begins to look alien. But because we don't understand the symbolic language, it now gets confusing. But the fact is, the algorithm is as simple as that. So look at all these examples we have here. A recipe, if you have a recipe, how many of us have like to cook? How many of us go online to look for recipes, or we ask our parents for a recipe, or you just cook whatever you like? How many people, mention it in the chat? I'd like to see. But by the time you follow a recipe to prepare food, it's an algorithm, because it's a step-by-step ordered sequence of tasks you carry out or steps you carry out, to accomplish a task or solve a problem. And if you don't follow those steps exactly, then something will go wrong. And that's exactly, what our algorithm is and how it goes. So, yeah, a morning routine. There are many other examples. So what I would like everyone to type in the chat is, give me another example what you think, based on this definition, what you may think could be an algorithm based on your understanding, day-to-day life. What do you think is an algorithm? So while you type that, you know, now in computer science, it is formalized and it's really specific to the context of software, development in computer science. We also have algorithms as a concept in mathematics, but in mathematics, it is for solving equations or solving systems of equations or solving things that are even more complex than, systems of equations. So in those cases, yeah, it is also steps you follow to solve those equations. But when you come to computer science or in software development, an algorithm basically gives you a sequence to follow in order to solve a specific problem. In fact, right now in the world today, there's almost no software that doesn't use an algorithm, no matter how simple. Even your own code that you write in JavaScript, what most people don't realize is that your own code that you write in JavaScript uses an algorithm, right? Or Python. By the time you are using a array.sort or array.find or array.filter or any of those built-in functions or functionality, what you may not remember or what you may not know is that the underlying implementation of array.find, for example, in JavaScript, actually uses an algorithm, or array.search, because it's a search algorithm. And we'll talk about some of the search algorithms when we go into details in the next classes. So as a programmer in today's world, you can actually get by without knowing anything about algorithms, but it is beneficial to you to learn it, because if not, you won't understand performance. You just write code and your code is going to be very slow and clumsy, simply because you have not realized that you have not realized the complexity of some command you are just using or some function or method that you are using, and you don't know how it will affect your code. Okay. Yeah. So this is interesting. Somebody said preparing Costa has a very specific algorithm. How about quicker oats? Temperature, even Gary, making Gary. There's a way you make Gary and it will make sense. The way you make Gary, it doesn't make sense. Right. Driving a car, so a lot of things that we take for granted. Okay, all right. So I'll talk a little bit about algorithms. The interesting thing is that what most people do not understand is that algorithms actually emanated, from India. Before this period that you see on this slide, we used to have a Roman numeral system. How many of us have heard of Roman numeral system? Who can tell me what is 50 in Roman numerals? Most people don't know that anymore, right? We only know the decimal system that we use now, the decimal number system. Well, let me ask, how many people like 50 in Roman numerals will be a letter, right? Like L. Okay. Then now imagine somebody wanted to divide 50 by 2. You do L divided by what? What will be 50 divided by 2? L over II. How do you solve that? In fact, what algorithm can you use to solve that? So then imagine 1993. What's 1993 in Roman numerals? Who knows? If I can remember, 1990 used to be MCM. Let me see if I can remember. What's 1990? 1900. So 1000 is M, 900 is CM, 90 is what's 100 again? C, XC. Okay, 1995. So 1995 VII. So let's this is 1995, right? Okay, 1995. Yeah, you got it. So 1995. Ha, that's 1995. MCMXCV. MCMXCII is 1994. Okay. So that's interesting. Now, if somebody were to say divide 1995 by 5 in Roman numerals, so assuming you were a Roman, and somebody they'll say, okay, divide by 5 equals to what? How would you solve this problem? How do you even, assuming you're a Roman and you don't know anything about decimal numbers or decimal notation of numbers, how would you solve this? It's just almost impossible, right? So when somebody in India came up with what we call a decimal system of representing numbers, right? So everything is based on 10, a number 10, which maybe coincidentally or not coincidentally, that matches the number of fingers that we have on both hands, right? And so they used 10 to represent numbers, and they said, okay, the lowest unit, we count as 1. Then when it gets to 9, we now add a 0 and becomes 10, and then we continue with 1 and we continue. And now everybody in the world, we understand this whole decimal system. But you see, the interesting thing with decimal system of notation was that it made it very easy to do arithmetic, because if imagine if I wanted to do in Roman numeral, if I wanted to do 4 plus 5, I'll do, what is 4 plus 5 in Roman? Is IV plus V. Well, you probably have to cram it. It'll be easy. But in Roman numerals, okay, 4 plus 5, that's okay. It's 9. If you were a Roman, you probably would have memorized it as well, that 4 plus 5 equals 9, right? But the problem with Roman numerals is if the numbers now become more complex, like 2, 3, 4 plus 1, 2, 3. Okay, this now becomes more difficult, because if I'm a Roman, who can tell me what 2, 3, 4 is in Roman numeral? That's CC, III, X, 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 IV. Okay. 1, 2. What's 20? 20 is just XX, right? So So what I just wrote now, that's this 234 plus 123 is what I just wrote. This is equivalent in Roman numerals. How will you add these two numbers, right? And this is the interesting thing, right? When we are doing when we are learning numbers, when we're learning about numbers, there are actually two ways we learn the numbers, right? And I want to ask everybody this simple question. If I ask you 1 plus 1, what's the answer? Do you need to think about it? You guys can unmute and speak. If I ask you 1 plus 1 or 2 plus 2 or 4 plus 4, right? You just know the answer.
No. I don't need to
So
think
why
much
do you
about it.
know? Why do you just know the answer? Because it is innate knowledge, right? That's what I call it. It's innate, it's specific, it's intuitive knowledge. You have memorized it. And a lot of us did that when we were younger, when we had this times table, right? 2 times 2, 1 plus 1, and all of that. But at some point, right, our knowledge switches from being the innate intuitive to being an algorithmic knowledge. So for example, I tell you 5 plus 5, or rather, let's say 5 plus 5, you know the answer immediately. You don't need to think about it. It is a primitive as far as numbers are concerned. But if I tell you 123 plus 875, can you tell me the answer immediately? Who can tell me the answer to this immediately?
I'll use
Give me the
calculator.
answer
I
in
can't
5
say it
seconds.
immediately.
Just type it in the chat. I want to know how long it will take. Don't use a calculator. Okay. So it's 998, right? But you see, it did not memorize the answer. Did you memorize the answer, or did you use the primitives and follow an algorithm? I want to ask, how did you arrive at this answer? Did you just think about it, or you had to calculate, right? And when you were calculating, what did you follow? You followed an algorithm. That's what you did. And that's the HTU algorithm, right? Which most of us, we learned it in school. Now let's go to multiplication. If somebody says 5 times 6, right? 5 times 6. What's the answer? You know it already, right? You don't need to think about it because you've memorized it. But now let's assume I'll give you another one. I said 8765 times 123. Can you tell me the answer? You have to calculate. In fact, a lot of people need a calculator for this one, right? But you can still do it with what we call the long multiplication rules, right? That multiplication rule, let me ask, is it an algorithm or not? It is an algorithm. So our knowledge is now, is of two forms. There is the innate knowledge, the memorized knowledge, and then there is the second one where it is not the knowledge itself that you memorize, but the steps. It's not the answer that you memorized, but the steps to get the answer. And the steps to get the answer are leveraging on the answer that the simpler form, the primitive that you had already memorized. And the reason why this is very possible is because of this decimal system, this base 10 system of counting numbers. So the interesting thing is that one very wise man that has this name that I'm trying to, it's an Arabic name because it's Arabian, Muhammad ibn Musa al-Khwarizmi, al-Khwarizmi. He was a mathematician from Baghdad. And what he did, you see all these methods that we are using now, this long division, multiplication, addition, he laid out all those methods for adding, multiplying, and dividing numbers, and even calculating square roots and calculating pi. And all of these were based on a decimal numeric system. That man did all of that and he put it in a book. And that book was printed and shared to the world. And that's what we consider as the first algorithms. In fact, the interesting thing is that if you guys pay attention very well, that man's name is algorithm. The word algorithm comes from his name, algorithm. So the Romans kind of Romanized that name and they call it algorithmus or algorithmy. That's his name, is what we now call algorithm. So that's did you know for you to take away from today. So it's interesting that what we now use to run tech in the whole world came from such a far place. Now, interestingly, right, they when the book that was written by this man, this list of methods for calculating, for adding, multiplying, dividing numbers, the knowledge was so small then, right? When he went out into the world and he got to Italy, and a man called Leonardo Fibonacci, continued studying what this algorithm had started, right? And he continued studying it, and eventually he came up with a series. Now, can you guys look at this series? Can you see this series of numbers, a sequence of numbers, 0, 1, 1, 2, 3, 5, 8, 13, 21, 34? What is this series of numbers called, for those who know? It's called the Fibonacci series, right? The Fibonacci series or Fibonacci sequence after the man, right? So look at this series of numbers. Now, what's interesting about this Fibonacci series is that there's actually an algorithm for generating this number. Who can tell me what the algorithm is? It's more or less just type it in, type it in, or go ahead.
Okay, it's gotten by adding, summing your previous number with the current one. Let's say we have 0, and you have, after 0, you have 1. So the next one will be 0 plus 1, which gives you 1. And the next one will be 1 plus 1, which gives you 2. And the next one will be 2 plus 1, which gives you 3, and so on. So it goes like that, adding your previous number with the one you have already.
Yeah, thank you. So the Fibonacci series is basically each n, f of n, is achieved by adding f of n minus 1, right, to f of n minus 2. So that is f of n in this case is the nth number in the Fibonacci series, and f of n minus 1 is the previous one in the series, and n minus 2 is the previous 2, the 2 steps back. So that's how you get it. But of course, f of 0, which is the first Fibonacci number, right, there's no number before it, so you have to start f of 0 from 0. And f of 1, you also have to start it with 1. So the Fibonacci series is now an algorithm that says if n, so depending on the value of n, if n is 0, then the Fibonacci number is 0. If n is 1, then the Fibonacci number is 1. But if n is anything else, then the Fibonacci number is f of n minus 1 plus f of n minus 2, right? And the interesting thing is that this series, a lot of people came to study this series, and they came to realize that a lot of things in nature actually follow this sequence, right? Or they kind of match this sequence. In fact, you can just go study Fibonacci series or Fibonacci sequence, and you will really understand a lot of things, a lot of interesting things about this number series. In fact, I have a sidebar here. The first sidebar was, okay, what's the algorithm for this series, which you just did? The second sidebar is, if I want to calculate the nth Fibonacci number, what's the algorithm to calculate the nth Fibonacci number? It's not as simple as it sounds. Now, if you wanted to do what we call a naive approach, right? how would you do it? You would just generate the Fibonacci series, right? And continue generating until you get to n, then you pick that number, right? But that's not, and this is where we now talk about, algorithms. When you're looking at algorithms, you look at several things, right? You look at one, is it correct? Does the answer that it gives you, is it correct? The second thing is, does it take a long time? In other words, is it even possible to solve it, in your lifetime or in realistic time, right? As a function of n. And then, yes, if we can solve it, is that the best we can do? Can we improve on that solution in terms of course, it's already correct, so that's not what we are improving on, but how fast can we solve it? So the whole pursuit of algorithms in the world today is really about faster and faster implementation. And a good example is that Fibonacci number. So if I want to calculate the 100th Fibonacci number, how many of you can calculate it for me? Let me give you a few seconds, right? I'll just pause. Maybe I'll share my screen. Let me see if I were to write a JavaScript to solve and give me the nth Fibonacci number. How would I do it? Let me switch and pull up my JavaScript. I can use anything. I'm looking for what. Yeah, I need some. Who can recommend to me what I would use for JavaScript, for code on JavaScript? What do they call that thing? Is it CodePen? Okay, let's go.
Yeah,
to
CodePen.
Yeah, so let's go to CodePen. So I'm going to switch to CodePen. Can you see my CodePen screen? I'm on there now.
Yes.
Yes.
All right. So I want to see if I can do a Fib. So the idea is I want to do the nth Fibonacci number, right? So console. Let me just test to be sure CodePen is working. Now I want people to, what do you guys think? At least they will just go with the naive approach. I'm not going to overthink it because I've not actually thought about it. How do you run stuff on CodePen again? Where's the run
It
button?
seems there's a console button at the bottom left. So it runs on it, so we can see the test here.
Oh, so how do I log stuff? It's saying console. Okay. Oh, okay. Okay, runs. Okay. All right. So if I wanted to generate a Fibonacci series, so I could say constant fib equals, we'll just start with this, or we have to start with the first two, which is 0 and 1. Then we can do just to generate the thing for each. I hope you guys item. Um, okay. So now let's take this off. Okay, my console is in login. I have to come here. Oh, well, this didn't seem to run. Repeat? Where is repeat?
Says repellent.
I actually thought this, well, so this has changed. Okay, I should use repo it. Okay, that's what you're saying. I have to create an account. Okay, let me do it myself then. Sorry guys, let me just do it PHP Storm. And you see this file now that is called testing. Hello,
Yeah, we can hear you, sir. Go ahead.
can you see this file called testing? Or
Yes,
this,
yes, I can see it.
okay, so I'm just using the console for it, basically. So we are just going to work with the console. All right, I'll refresh the page whenever I need it. Let me also share my PHP Storm screen so you can also see my PHP Storm screen. Okay, so right now I'm just logging this. Okay, so we have it here. Now, what I was trying to do then was just so Fibonacci series, you start with a 0, you start with a 1, then you can do a fib dot for each, then item. Uh, who is Anthony Star? You are, why are you requesting control on my screen? Okay, so all right, so these are the two numbers in the Fibonacci series. Now, normally what you would just do is the Fibonacci series generation. So for maybe let I equals 0, I is less than 100. So let's assume I wanted to generate 100 Fibonacci numbers. Then I would say fib dot push. Fib. So remember the algorithm is the previous two. So we already have the first and the second. So we'll start from 2. So I minus 1 plus b I minus 2. So are we following? This is a simple algorithm. So I'm just trying to demonstrate to you what, when you say an algorithm, it can be as simple as this. This is just a simple algorithm to generate a Fibonacci series. So we start by creating the first and the second numbers, and then we run the algorithm. So one skill we need to learn is how do you convert an algorithm into code. So you don't need to even be an algorithm designer. Sometimes somebody can design an algorithm and give it to you to code. The question is, can you code it? How fast can you code it? So a lot of times when you go to algorithm competitions, you are basically just going to have to code really fast, right? Now, I refresh this, and you guys can see it has generated the first 100. Can you see it? Just say yes on the chat if you can see it. I needed to log item index. Hello, can you hear me?
Yes, we
Yes,
can
I
hear
can hear
you.
you, sir.
Okay. Okay, so we have the first 99. Well, it's 100 since we started from 0. So now, if I were to try to time this, right? if I want to get the 100th Fibonacci number, then let me Kukuma put it in some div here and say id equals display. Somebody is trying to control my screen. I wonder why. Who is Anthony Star? Take control of your phone so you don't distract this. Okay, so so I can put all of this into a function, right? Let's call it calculate the nth Fibonacci, and then I supply the n, right? And then I move all of this in. Then I can use the long process. First of all, I've generated it. Then I can do a reduction, fib.reduce, right? Item, item. I beg, who knows reduce? When we are reducing, what comes first? Is it the item or the total?
The accumulator before the total. The accumulator before the current. Accumulator, then current.
Okay. Yeah, that's how you know people who are JavaScript gurus. So you return this, right? And did I miss something? Immediately I said return, I think. Okay. Guys, give me a second. Okay, so can you see I'm on trying to figure out why my okay. Okay. All right. So I have a function now. So if I want to um so this is me doing it really quick, right? Hello, are we there? We had a little bit of we had a little bit of interruption, but we dealt with it. Okay. So you can see that I'm getting undefined. Okay. All right. Um okay, don't mind me. All right. So oh, sorry. This is the sum of Fibonacci's. This is not what I want to do. Okay. All right. So that's the third Fibonacci number. Okay. So let me now add some stuff here. Anyway, let me not spend, I'm not supposed to spend this whole time writing code. Today is not the day for writing code, but I just wanted to prove a point. Like if I want to do Fibonacci of the hundredth number, this algorithm, what it's doing basically is it is calculating all of the 100 Fibonacci numbers and then returning it. And that is not the most efficient way, but it's a naive way, right? So it calculates 100 of them. If I wanted 1,000, right? I'm not timing it, but I wish I had a time to time it. We can do this as an exercise later, right? It's now counts doing the 999, right? And it's giving me this number and it will go that way, but it is not the optimal way, right? So let me just go back to the presentation. So essentially, right, that is a naive way of solving an algorithm, which is basically the simplest idea that comes to your mind, but it's not always the best. So one thing we have to understand is that the simplest idea that comes to your mind and the simplest implementation is not always the best. So you need to think deeper. That's really what that exercise was about. But it was also to tell us a little bit about the Fibonacci series. Now, talking about algorithms, right? Most times algorithms actually boil down to these basic activities, right? The types of algorithmic problems that you may have to solve. Either you are sorting a list, you are searching through a list, or you are testing if something meets a criterion. So for example, if you want to test if a number is a prime number, in fact, primes are one of the most difficult numbers to deal with. In fact, the whole cryptography thing, for those of you who are doing cryptography and cryptocurrency, is all based on the difficulty of finding prime numbers, you know, or generating prime numbers. Of course, if a prime number doesn't have more than 2 factors, that's what makes it a prime number. Hashing problems, yeah, that's really cryptography, finding large prime numbers. Then you have combinatorial problems. So these are problems that are a combination of different other things, you know. So the way you would solve them would be by essentially breaking it down, right? Then numerical problems, these are problems that have to do with numbers that you can break it down into an iterative set of numbers. Then optimization problems are problems where you try to get the simplest or the fastest or the most optimal solution. Optimal can be the highest or the lowest, depending on the parameter that you're trying to optimize. Then you have what we call NP-complete problems. I'll talk about that later. But NP-complete basically, so okay, if we look at it, this other part of the slide, right, you see, apart from that, we also have another way of categorizing problems. A tractable problem is a problem that you can solve in polynomial time. Polynomial time basically means you can solve it. The time it takes to solve a problem is proportional to the number of iterations that you have to do, or the number of data items that you're going through. So for example, if you are searching through a list and your list has 3 items, the length of time it will take you to search through it is proportional to 3. If it now increases to 10 items, the length of time it takes you is now proportional to 10, right? That's tractable. So the complexity or the time it takes is proportional to the number of elements in that list. But an intractable problem is the one where the time it takes you to solve it blows up exponentially, you know, with the number of elements that you have to search through or sort or test or whatever. So remember, really, at the end of the day, our algorithms boil down to list of items or a data structure that contains items, which you have to either search through or sort or do some other kind of optimization. And that's why algorithms are always very tightly integrated with data structures. If you don't understand data structures, you won't be able to understand algorithms. Then we have the NP, which is a non-deterministic polynomial solution. That is, you can solve it in polynomial time, but your answer, okay, you can only guess it. You are not sure that that's the best answer, right? While an NP-complete problem is an NP, a non-deterministic polynomial problem, which you can reduce to a form that is similar to other NP-complete problems. So what that means essentially is that they are similar in how those problems are. And when you solve them, you can use that same solution for all of them. All these things sound like jargon, but I would encourage you to learn them. And over time, you understand what they mean. Okay. Do you have any questions so far? Any questions? Okay, if no questions, we'll move on to the next slide. Now we're talking about, okay, we have these different kinds of algorithmic problems to solve. How do we solve them? What kind of approaches do we use, right? So we have a brute force search, or the other name you can call it is a naive approach, which is what we just did with that Fibonacci series. Basically, just search everything one by one until you find what you're looking for, or sort it by taking one. They look for the lowest number. So for example, a naive sorting algorithm would be, I have a list of numbers and I'm asked to sort this list of numbers. What I do is I look for the smallest number first. I pick it, I put it at the top of the list. Then I go look for the next smallest number. I pick it, you know. That is not a very efficient algorithm, but that's the simplest. That's what you would call a brute force. So it's always simple. You always find the solution, but it is not feasible in most cases because as a size of the data sets that you are searching or sorting or the data set you're applying that algorithm on, as it grows, it blows up exponentially, the number of times you have to do. And when we talk about blowing up exponentially, when we are doing big O notation in a later webinar, I'll explain to you why it blows up. It will be very easy to understand. Then, of course, we have divide and conquer. Divide and conquer basically means you take the problem, you break it down into smaller parts that are common, and then you keep repeating those parts. And that way you can solve it faster. A greedy approach is don't think too far ahead. Just pick the best option in the next iteration and keep going, right? This works in some cases, but in some other kind of search, it's not the best, because when you pick the best option now may not be the ultimate best option, right? Then dynamic programming, which is a method where you actually use some analytic methods, to solve it. So those ones, it's a very powerful tool because it's applicable to a lot of different kinds or categories of problems, but it's also difficult for you to understand. You need to study it very well. So you may not even use it that often. All right, then we talk about big O notation. We will go into details about big O notation later, but big O notation is basically a way of representing the complexity of an algorithm or an algorithmic problem. Or the complexity of an algorithm, and by that, how long it will take, or a measure of how performant it is. So it's used to determine whether an algorithm is going to take a long time, depending on how large, your data set is, or it will take, whether the time it takes to blow up, exponentially or not. So this is what big O notation is all about. And a lot of people, you also need to study big O notation a lot so that you will be able to get a better understanding of your algorithms. And when you are applying it, you know how to apply some of the library functions that we get. When you use a framework or something, you need to understand this function or this method. What is the complexity, So just a summary of big O. When we say something is big O1, that means it is constant time. What constant time means? It does not depend on the number of items in the list or in the data structure. No matter how many, it will use the same amount of time to complete that algorithm. So this is the best. If you can actually get your algorithm to run at constant time, that's the ultimate, right? Then the next more complex one is the big O log n, which is basically saying that the complexity increases with the log of the number of items. So it is more complex than the big O1, but it's less complex than polynomial. A polynomial is the next one. Polynomial depends on the number of items, but it doesn't just depend. It could also be a power of the number of items. So when we talk of polynomial complexity, that is saying that it is a power of the number of items in the list that you are applying the algorithm on. So, and the higher the power, the more complex. So that's why they say the big O complexity of n raised to power 5 is more complex than n raised to power 4, and so on. Then the last but not the least is the exponential. Exponential is when it is not n raised to power something, but rather it is something raised to power n. In most cases, we use 2 raised to power n. So this is the type of complexity that is so large, it blows up so fast. It's not really good. In most cases, you always, if you do an algorithm and it's complex time, right, you want to go back and redo it and see how you can improve on it, right? So that's exponential. Then you have a factorial. So we all know what factorial is. Factorial is another thing, just like Fibonacci series, that you can use. But the good thing is factorial actually, factorial, you need to use a loop to calculate it as well, because it's multiplying a number by the number previous to it. Okay, so But a factorial, funny enough, has a greater complexity than exponential because it blows up faster than an exponential will blow up. Okay, so these sound very like mathematics and so on, but you guys should not be worried. We'll get to the part where, this is just jargon, right? Once you understand the jargon, you can move along with it. The concepts are not difficult. The concepts are simple, okay? Okay. So now let's go to the part that really, affects us, right? There are three key programmatic constructs. So what I mean by programmatic construct, when you are building an algorithm, because an algorithm basically means repetitively doing something in most cases. You have a sequence of steps, but most of those sequence of steps would happen in a loop. So the most important programmatic structure or construct that you need when you are building algorithms are loops and function recursion. By the way, function recursion is a loop. A function recursion, how many of us realize that? Or how many of us even know what recursion is? If you know what recursion is, just type yes in the chat. I want to see how many people. Tell me what is recursion?
A function that calls itself.
Okay. A function that calls itself. So if a function calls itself without a condition, a stopping condition, what happens? It's the same thing as an infinite loop, right? Because an infinite loop also can be, you can also have a loop that doesn't have a stopping condition. So in all cases, you must have a stopping condition, whether it's in a loop or function recursion. And that's why number one is important. Number one is a conditional that will stop it. Okay. Now, what most people may not realize is that recursion and loop more or less can achieve the same thing. So let me show an example. Let's go back to, I calculated the Fibonacci and I use a loop, right, to generate, I use a loop to actually generate a Fibonacci. Now, I want to ask this question. Can we use recursion to generate this Fibonacci number, the Fibonacci series? And how can we do it? Let me show you how. And I love recursion because recursion makes code very concise, right? So assuming I wanted to get nth Fibonacci with recursion, right? And I put n. Now let's think about it. And this is an interesting exercise because most people may not realize that, when you are doing a recursion, you need to think about it because the first component of recursion is that I'll call the function from within itself. So I'll call the function again, but I need to pass in a different number. If I pass in this same n, I'm just calling it on itself. So let's assume I did a console log, right? Now let me take this one off first and then just do this. And let's say I want to get the 9th Fibonacci. I'll actually end up with an unending loop here because I'm just calling this thing by itself. I'll just keep calling it. It will never stop. If you look at this, you see it keeps running. That's why we say we have to have a stopping condition, right? Okay, so already JavaScript and the browser have helped me out by shutting me down when I exceeded the maximum stack size, okay? Now, so you need to have a stopping condition. So typically a stopping condition is I have gotten to the number I want to get to, right? So let's say now the way you do it is that when you are calling it, you either decrement or increment the number. So that it calls with a different number. This still doesn't have a stopping condition, so it will not stop. The only thing is that the number will continue to reduce, right? And you see it has already gotten to a negative number. So that means I needed to include a stopping condition. It started with 9876 and then it got to 0. Now, what should I have done? I should have stopped it at 0, right? So that becomes a stopping condition. So how do we stop it at 0? We just say if n is greater than 0. We call it again. That means if n is, once n gets to 0, it will not call itself. So it will stop there, right? And so we will get it running to 0. So that's the most important thing we need to realize, just like in a loop. In a self-calling recursive function, it needs to have a stopping condition. Now, but I only did a stopping condition. I've not solved the problem, right? For me to get the nth Fibonacci, I actually cannot start from n because Fibonacci starts from 0 and goes upwards. So I need to start from 0 and go upwards, right? So so I can introduce a variable current and say, okay, 0, give a default value of 0. So I'm still getting to n, but now current will be increased. Current, let me increase it first. So current plus, right? Or let's do plus equals 1. So you increment it by 1. And then we are no more, since we are not changing n, we are changing current. We'll now say if current is less than the number that I'm getting to. So if it's less than n, I will call it again with the new current. Oh, haha. All right, that's good. So it's now current that is changing. That is the current number I'm doing. So if I do get n Fibonacci for 9, yeah, so I'm now counting upwards, but it's not calculating the Fibonacci number. So now to really calculate the Fibonacci number, we can now we have to keep a count, right? So if current is 0, we can now do a switch because we have 3 situations. We have when current is 0, we have when current is 1. So when current is 0, we now return I need to keep a sum too. So let's I need to keep a sum. So let's keep a sum. So sum okay, so sum is 0. Break. If it is 1, sum is 1. Break. But if it is anything else, I'm sure there's a better way to do this, but let's just do it the naive way. Oh, I think we need to put in the sum here and not keep it here. All right. So if current 0, sum is 0, else sum is 1. we still need to keep we need to keep track of it. Okay. Series. I'm doing this thing in real time, so I'm thinking of the series. So still the same thing. If it is 0, we series starts off with just an array that contains 0. So now instead of trying to do the sum, I'm just doing a series. I'm generating a series of Fibonacci starting. So on the first attempt, we put in a 0. On the second attempt, we already have a 0 in it. So we now put in the 1. On the third and subsequent attempts, we now push the previous one plus the previous one before the previous. Okay. So I hope that is clear. And at the end of the day, we return, if current is less than n, we call the next one. And then when we finish, well, we need to also push the series. And then at the end of the day, return the series. So this is essentially just generating it. But this is not okay. Series. But we can also log the series. Okay. This is using recursive. Let me see what I get. I get nans. Why do I get nans? Okay. This is a problem. I shouldn't have incremented current until when I'm done with all of this. But this is assuming current is 0, 1, and then other things. Okay. So we get again a Fibonacci series. Let me log this before I return it. Okay. Oh. Okay. You see where you put stuff. And this is one very interesting thing, right? When you are using recursive functions, the value changes depending on whether you are doing it before the recursive call or after. Just logging this same thing after, I get a different thing. I get the same thing all the time. So one needs to understand how recursion works. Otherwise, but putting it before, I get the correct thing. So this is using recursion. I hope you guys are seeing both the PHP Storm screen where I'm coding and also the where I'm testing it.
Yeah, we can.
Yes.
Okay, so I think I'll pause here because there's a lot of quietness. I want to hear what what you guys have to say. Questions, before I move into the last part of it, which would be basically, I would like us to do some exercise and I would like people to try it out, right? Before I go into talking about the last few things. So do you have any questions on what I just did now? I was just trying to demonstrate the three aspects that you need to know in order to be able to code out algorithms. You need to know conditionals, you need to know loops, and you need to know function recursion. So any questions before we move to the next slide? Do we all understand? Or is it too complicated? Okay, so I'll take it that we are following. So now I already mentioned for you to really be able to write algorithms, you need to understand data structures because every algorithm is actually tied to a data structure. Most algorithms are actually implemented on a specific kind of data structure, right? So, and what's a data structure? A data structure is basically a collection of data. There are three definitions here. A collection of data that allows you to basically manipulate values, manipulate informations. It allows you to store them and to manipulate them. Okay. The other way of looking at it is it's a data organization, management, and storage format. So it's a format that allows or enables efficient access and modification. Another way of looking at it is it helps in organization of large quantities of data, make it easy for modification, for search, for sorting, filtering, and so on, right? So data structures are needed for you to properly understand algorithms. And in most of the cases we work on, most complex algorithms will use a tree or graph data structure, but we also have other data structures like linked lists, arrays, linked lists, and so on, which we will use. So what you see here is a summary. This is not an exhaustive list of all the possible data structures, but this is a summary of it, right? So you have an array, which is an ordered set of information, of data, and is always in a contiguous memory location. When we say contiguous, it's continuous. That's what it means. It's just big grammar. It means continuous. Then a list may not be ordered. So you have types of lists, and it may not be in a continuous or contiguous memory locations. Okay. Then a tree is basically a list that has additional, in fact, a more complex list, basically. A list where each parent has multiple children. We can explain all of that. A graph, right, is a tree. I won't go into all of this. Today is not really about data structures. This is just an introductory. So you just read this and just, take it as you see. In those days now that we used to, when we were in school, you don't understand something, they say, no worry, you don't need to understand, just take it like that. But what I will tell you all is that you understand over time. So don't be too worried about it. This is an introductory session. So I'm just trying to throw all the concepts there. Okay, so that's algorithms, right? So let's talk about some things that we can relate with. I gave examples. I asked earlier, what are the things that you can call algorithms, that you do? And most people were saying cooking food using a recipe. Yes, that one is there. But did you know that tying your shoelaces, you're using an algorithm actually. When you decide how you want to fold the lace, classifying objects. If somebody gives you some objects, the red ones, the blue ones, the green ones, and they say, okay, separate them. You are using an algorithm actually. Your brain is using an algorithm. It's just that that's why most of us we underestimate our brains. We just do things without thinking. Man, how is my brain able to do all of this? Well, that's what it is, right? Bedtime routines, the things you do before you go to sleep. Or if you're in a library or in a bookshop or even in a shop and you're looking for some particular thing, how do you find it? Did you people know that that's a search algorithm actually? You are doing what we call a bubble sort or a bubble search. No, a linear search. When somebody gives you something and say, go and look for this thing, what you are doing is you take the thing, you look at it, you go, you compare. Is this what I'm looking for? No. You go to the next one, you compare. It's a naive approach, right? But that is like a linear search. You are just going there, checking, checking, checking. In fact, deciding what to eat, right? We are thinking about it. What should I eat today? That's that's an algorithm. In fact, I want to refer you guys. I'm not going to talk about the numerical ones because we've talked a lot about Fibonacci, prime numbers, and all of that. So I'm not going to go into all of that. But these are also other kinds of algorithms. I know most of the time when we read and study algorithms, people always bring mathematics, Fibonacci series, prime numbers, prime number tests. How many of you have heard of LCM and HCF? Do you know that that's an algorithm also? Or even searching for a word or checking in a dictionary for a word. That's an algorithm, you know. So wherever you are following, people are saying that when you are checking baby is also algorithm. I would agree because one thing is if you don't follow the right procedure, then it will fail. And that's what an algorithm is. Also, your algorithm could be complex, exponential complex. That one means if it is exponential complex, you never succeed because by the time you finish the whole thing. But if it is complexity big O1, that's a fast one. So in life, we are always dealing with algorithms. In life, we're always doing things. It just seems difficult when we now need to take it and formalize it into a step-by-step process that we have to write the code for it. But that is something we will have to do. Okay. So I'll end this presentation by just asking this question. What are the daily situations that involve use of algorithms? In fact, let me show you guys. There is a post on Quora, a very nice post that one guy posted. I think I put it on my. Let me see if I can find that post. I'll show to you somebody that was kind of citing the different types of what they do. When we're saying what is an algorithm, what is an algorithm? So I'm going to copy this and I'll put it on the slide so that people can see what the person considered as, situations where they use algorithm. This is on a lighter note, but it's very interesting. So I'm going to put it up. Situations where you can use algorithms. Since, well, for the ladies, this is also applicable to men as well. So don't feel left out. I'll put it up in a few seconds. All right. So the question is, how often do you use algorithms? How often do you use algorithms? And can you all see my screen?
Yes.
So let's look at this. Number one, on the way to your college canteen, use an algorithm called A star search. Then when you are waiting in the line in the canteen for food, well, it's not really an algorithm, it's a data structure called what? A queue. But there's also an algorithm that runs that queue, which is, you know, the person at the front, when they get the food, they move on and somebody else joins at the back. Then how do you notice the girl that is standing in front? You do a linear search because you are just looking for interesting people, right? And for girls, I know girls also look for interesting boys. So you do a linear search. You look at each face one by one, starting from the one closest to you to the one farthest from you. Then searching for her dad in the phone book, you use binary search. Then you Google it. That's a tree search. Then you search for her on Facebook. Facebook uses depth first search. So when you are doing that, you're already using an algorithm. Then when you find her, you do a friend request and it's accepted. Graph. Facebook uses a graph, by the way. And writing her a secret love letter using a cipher that also uses an algorithm. Then when you upload your first pic, that's image compression algorithm. Then when you look through WhatsApp messages, that's KMP algorithm. Then when you look through our WhatsApp messages and she finds out you people fight, then you start over with some gifts. They call that one backtracking algorithm. And when you get her a list of items to buy as an array, if the items are too many, she gives you a list and the items are too many and you don't have enough money. So you prioritize. So that is a queue. You do bubble sort. They making her play treasure hunt, linked lists, stack. Then you bring a ring and the family does not agree to your proposal when you propose to her. How do you solve that algorithm? You use what they call divide and conquer, which is a recursive algorithm. Then when you get married, congrats. For you to go to honeymoon, you need to optimize your traveling routes. So you use a traveling salesman algorithm. Then when your mom is packing luggage, you use what they call a knapsack algorithm, which is basically how can you maximize the content of your bag while minimizing the weight of the bag. Then hash table is when she packed your favorite pickles. Driving to the airport is breakfast search. So by people, we use algorithms every day, both the one that you are using in your brain, the one that is in your app, whether it's Facebook or WhatsApp or Google. But that's the interesting thing. So I just want to end it with this. And I'm ending it with this so that, I don't want us to end this thing with mathematics and Fibonacci, but let's end it with stuff that will encourage you to come back the next time. But what I can guarantee you with is, it is not hard, right? All you need to do is understand the terminology. And in no time, you guys will be tackling algorithms. So that brings me to the close of my presentation. I still have 20 minutes for any questions or discussions. Thank you for listening.
Okay, thank you very much, Aniebiet, Udoh. Wow, I think all I can say is wow. Please, let's just, of course, we're on Zoom. Let's just give a round of applause, please, to Aniebiet, Udoh, for this session. It's really been in depth. It's eye opening. I think, of course, this last place is the highlight. The fact that we basically just live it with algorithms. Everything we do, like it's just algorithm. And of course, I think I'm going to take what this person said. I think Victor, how number 10 has actually ruined a lot of things, the KMP algorithm, but it has actually not, I don't know if it has actually solved any problem, that algorithm, looking through WhatsApp messages. That now algorithm has destroyed a lot of things. So, but that's by the way. So please, do we have any questions? If you have questions, please raise your hand, and then I'll ask you to unmute. Please, if you have questions, raise your hand. But of course, just for informational purposes, this is just the introduction. Okay, it's just the introduction. We have a lot more in this series that would actually set you on your way to becoming very, very handy with algorithms and data structures, and of course, prepare you, for interviews, because of course, in most interviews for developers, you get to meet questions on algorithms and data structures. So this series is meant to actually help you to, have a certain level of confidence. Okay, so if you have any question, please, you can raise your hand and then just take that quickly. Okay, so Tosin says, does every programming language have their own algorithm or just a general one? So Aniebiet, Udoh, I think I'll leave that to you.
Yeah, algorithms are general. If you have solved an algorithm it solves problems, it has nothing to do with programming languages. The only thing is that the implementation of that algorithm, yes, you have to write each one in its own programming language, but it will be the same algorithm. So for example, if you discover an algorithm for example, a knapsack problem or traveling salesman problem, is the same algorithm. It's just that you now go and write it in JavaScript so that maybe there'll be a JavaScript library for it, or you write it in Python or write it in PHP or whatever. The essence of it is that after you've written that library, nobody else needs to do it again. So the value of it now, and that's the thing, right? The reason most of you are not dealing with algorithms because over the years, the so many years that people have been writing algorithms. These algorithms are now part of a lot of the programming languages. So you don't need to rewrite them. You just use the method, just like this Fibonacci I wrote there. If it's now incorporated as part of JavaScript, for example, or a JavaScript library, then you don't need to write the whole thing yourself. You just use that library. And that's why a lot of people don't need to deal with algorithms, but you can still be, a programmer and write code and deliver your, websites or your apps or whatever. But like I said, it's good to have that knowledge. So algorithm is language agnostic. It has nothing to do with the language, but the implementation will be done in each language separately.
Okay, thank you very much. Thank you very much. Okay, any other question? I think before we call it timeout. Any other question? Okay, so in the absence of none, I think we're going to call it timeout. So thank you very much, Aniebiet. Thank you to everyone for joining. So we're going to give you, of course, we'll inform you when the next session is going to be. So just be on the lookout on our Discord community or the Telegram channel. It will let you know when the next series, the next part of the series will be taking place. Okay, but until then, thank you very much and have a wonderful, wonderful evening.